All right, let's start. Good afternoon, everyone, and welcome to today's DAA seminar. Our speaker today is Professor Greg Herczeg. Greg is currently at the Kavli Institute for Astronomy and Astrophysics at the Peking University, Beijing. Just to give you a brief career. Okay. There was some echo, sorry. Greg obtained his PhD degree from the University of Colorado Boulder in 2005. He then moved to Caltech as a postdoc, where he worked with Lynn Hillenbrand, and then to Max Planck Institute of Extraterrestrial Physics in Garching, Germany, where he worked with Yevina van de Schouw. He moved to Kavli Institute at Peking University at the end of 2011, where he is now an associate professor and associate director for science. Earlier this year, Greg began serving as the chair of the Science Advisory Committee for TMT and started a position as science editor for the AAS journals. Greg's primary research interest has been in the area of star and planet formation. He studies problems associated with this field by primarily using observations in the UV through submillimeter wavelengths. His specific expertise is in the area of disk accretion and accretion-driven outflows. Today, he will talk about various stages of star and planet formation, describing the progress made in the recent years, but also highlighting the current gaps in our understanding. Greg, the floor is all yours.
Great. Thank you so much for inviting me. I'm really pleased to be here. I guess that's what I'm supposed to say. I was actually really hoping to get to India this year. And so I'm not accepting many talks, but I really wanted to give this one because I was hoping to bounce around a few places in India, and but due to my busy travel schedule, I wasn't able to get there. So instead, there's this talk. So please do feel free to interrupt me if you have questions. I can't really see who is raising their hand or anything.
No, so I will direct the question to you, Greg. So you go ahead with your talk. I will let you know.
Sounds
so
perfect.
Your hand, and
yeah, and
sorry, Greg, you're muted.
Oh.
Yeah, sorry.
Yeah. I think you.
Okay, go ahead, please.
Okay. Anyway, so I think some of you know I'm at the Kavli Institute for Beijing. It's possible that we have a few postdocs on the line who are currently there, except are actually now in India. We have 40 postdocs, so it's really a very large postdoc program. We probably have about 7 or 8 right now from India, and so it's really great place for if you're a student or a postdoc looking to looking for a job. We have jobs every year. Please email me. My email is down below, and I'll also put it on in the last slide. So if you're interested in postdoc positions, we have quite a few people, and especially quite a few people from India. We've had great experiences with Indian PhDs, and so we'd like to bring in more. So this talk, I'll be talking about what I think of as the last astrophysical step of our origin story, right? So in astronomy, we're always talking about our origins as a way to frame cosmology or whatever else. For us, star and planet formation is the last astrophysical step of our origins, and then geology and biology take over. And so the question for star formation is, how does material in a dense, clumpy interstellar medium turn into stars and protoplanetary disks that then turn into planets with the right chemistry? And so the way that we start to answer this question for this talk, I'm assuming that we already have a dense interstellar medium. So you can give whole talks on uncertainties in how you get a dense interstellar medium where stars start to form. So we're going to start at that stage. And this is an example of one of the most famous star-forming regions within a kiloparsec. It's Serpens or Aquila Rift. And you can see, if you're looking at it in the optical, there's a huge number of stars in the background. This beautiful image is actually from an amateur. And then there are regions of very dark places where there are no background stars. And so those dark places are all places where you have optically thick dust extinction. So that's the molecular cloud, where the dust is absorbing all of the background. And so how do we create a picture of star forming regions from looking at images like this and at other wavelengths? The star forming region is primarily composed of a few different things. First, you have the cold ISM, so dust and gas. On the edges, there'll be a lot of diffuse gas that is part of the cloud. And then as you go to the darker and darker regions, you get to denser and denser material. And then you have protostars that are still in the active forming. And then you have adolescent stars, which formed within the past few to 20 million years that are from recent bursts of star formation. So how do we create this picture? To look at the dust and gas, usually people go into the far infrared and submillimeter, especially for the densest parts of the cloud, where you have active star formation. So this is an image of the same region, but now in the far infrared instead of the optical. So in the optical, we see all of the dust is a dark cloud extincting everything in the background. In the far infrared, that dust lights up. So the far infrared, we see all the dust in emission. The dust is cold, so the peak of the black body is at long wavelengths, but there's huge surface area, so that means that we see all of the dust in great detail. So this is the same region, just in far infrared, and from this we can measure the dense dust that is actively forming stars. And we see now, instead of one huge cloud, there are a lot of little clouds. There's a lot of filaments in there. And then, so this is now back to kind of an uglier optical extinction map. And you can see exactly where these same regions are in the far infrared, and in the optical is an extinction map. It's actually like a star, or this is from stellar extinction from Cambrai-C. And then we need to add the protostars in disks. And so usually this is done through infrared or X-ray surveys. These stars are still very young, which means that they suffer from a lot of extinctions. They're hard to see in optical surveys. So you need to go into the infrared or X-rays to pierce through this extinction. And so people can find protostars and disks through these surveys. And then if we want the slightly older population, we can use Gaia. And Gaia then gives the population of stars that is no longer extincted. So these stars are a little bit away from the clouds. They're a bit older, typically 5 to 10 million years instead of 1 million year. And so we take all of these components together, all of the disks, protostars, adolescent stars, all the dust. And then we also want to fill in the lowest mass components. And so this is some nice work on the same region by Jessie Jose, where you can see she's using a water index. So at Mauna Kea, you can actually observe in the water bands between J and H. And those water bands, the same bands that you usually have telluric absorption, unless you go to a great site. You also get those same bands in absorption for cool brown dwarfs. And so she can identify the very lowest mass part of the IMF through this band, and then followed up spectroscopically, identify brown dwarfs and planets. And through all that work, we can come to this basic picture of how a protostar forms and evolves. And the timescales involved, we can estimate just by counting the number of objects and assuming a constant star formation rate. That's not quite right because star formation occurs in bursts, but we can still get an idea for how long these stages last. And so for protostars, they start out growing from very dense balls of dust and gas. And so for these youngest objects, all of their emission from the accretion, from the growing protostar, all of that emission is absorbed by the envelope that surrounds the protostar. So it's absorbed by all that cold dust. And then the cold dust re-radiates all of the emission. So you see the same luminosity as you should, but all of that luminosity is reprocessed to longer wavelengths. So protostars.
So Greg, there is a question. There is a raised hand. Manvi, you can go ahead, unmute yourself and ask the question, please. Another person has raised the hand. Manvi, can you please ask your question?
Yeah, I'm having trouble.
There's no
hearing.
response. You go ahead. Yeah, we'll see later.
Okay, perhaps they could write it out and you could ask, because I have having trouble hearing them.
No, I don't think they are still on mute. So you go ahead.
Okay.
We can come back to this later. Yeah.
Sounds good. And so then a protostar grows from this very dense ball of dust and gas. As with all astrophysical accretion processes, there are strong outflows. Those outflows start to erode the outflows. Manoj did some great work on this with Herczeg back a decade ago. And then eventually the envelope dissipates completely. What you're left with is a protoplanetary disk. And then from that disk, you form planets, hopefully. And the envelope stage lasts for a few 100,000 years. And that's when the star gains most of its mass. Once the envelope disperses, you have a protoplanetary disk, and that usually lasts for a few million years. And so for the rest of this talk, I'll be discussing kind of problems that I find interesting, whether you do or not, I don't know. But they're problems that I've found interesting and been thinking about over the past few years at each of these stages. And so each of these problems should give you a little bit of an idea of the types of things that people are thinking about in terms of where are the uncertainties and how are we trying to solve those uncertainties at each stage. So this is kind of like, I'm just skimming a bit in each of these stages to give you an idea of how stars and planets form. So I said that stars gain most of their mass during the protostellar phase. In this cartoon, you can see that the star is very deeply embedded in this infalling envelope. So you have accretion from the envelope onto the disk. You have accretion through the disk onto the star. You have outflows that could create cavities. And most of that luminosity that's being released is from, converted from the gravitational infall. And it occurs mostly at the star. And the total luminosity from the star, from the accretion, is buried in the envelope. So it's very difficult to see. Typically, when people want to measure what's happening for a protostar, the first thing they'll do is get a spectral energy distribution and plot it up and see what the bolometric temperature and bolometric luminosity are. So the bolometric temperature is the temperature where the SED peaks. It's usually very far in the infrared, and then L-bol is just luminosity. So this is the type of thing that you can measure for protostars relatively easily. Right? There are all kind of other complicated things, doing chemistry and a lot else, but this is kind of the first thing that people do. And that's led to what we call the luminosity problem. This first was identified by Scott Kenyon in 1990, but then with Spitzer selected samples by Mike Dunham and Neil Evans, it really hit home that this luminosity problem is real. And what it is that protostars are too faint. So if you look at this, what we call a BLT diagram, bolometric luminosity versus temperature, you can see that there are a lot of stars, a lot of protostars here in red, and then as they get older, they move to higher temperatures. And all of the protostars in red are fainter than where the models predict they should be, which is the shaded region. This diagram is a little bit complicated to understand. It's in 2 dimensions. My brain is very one-dimensional, either because I'm simple or because I'm a spectroscopist, or probably both. So instead of 2 dimensions, I like thinking about this in a 1 dimension. Mike Dunham was kind enough to collapse this down to a single dimension. And you can see the plot on the left. The models predict luminosities that are much brighter than what the luminosity should be otherwise. But if you add in variable accretion, so large bursts that are very rare, you can make these 2 distributions.
Greg, there is a
agree with each
question.
other. Yep, great.
Mike, please go ahead.
Yeah, Greg. So these models, what are these models based on? Is it just an informal model, or does other physics go into these models?
So they start with a shoe infall model where you have a steady accretion rate through time, and then they add bits of physics to it. They add outflow cavities, and they show that none of that works. But what does work is variable accretion. Their version of variable accretion was these very large bursts. But Hop's work that Manoj was involved in showed that the variability didn't have to be in bursts. You could get an exponential decay. So it's still, it's a little bit unclear whether you really need these large bursts or not. But what I think is clear is that you really need some sort of variable accretion, whether that's in a smoothly decaying, exponentially decaying accretion rate versus time, or in large bursts. It seems like that's the best way of solving this problem. And what that does is it puts most objects below these shaded regions because the bursts or that first part of your strong accretion is very rare. So then there are very few objects that are above these shaded regions. It's unclear why you'd have such large accretion rates in the Hops-Fisher sample. Why you'd put all the accretion early, but that's kind of a question for the physicists. This works out pretty well for observers.
Oh, okay, thank you.
Mm-hmm. Yeah, good question. So plausible kind of accretion rate history versus time is this plot on the right by Jehan Bey, where you see this is models of the accretion flow. And you can see that the accretion rate, it starts out very large, and then it spiked. There's a lot of bursts in the first few hundred million years. And that's when the star gains most of its mass. And then there are a few bursts later on. So this suggests that if we want to understand the earliest stages of protostar evolution, when the star is gaining most of its mass, we need to understand these bursts, and we need to look early in the life of protostar. We know historically that these large bursts occur. These are some famous light curves. Fu Ori is an object that has this beautiful light curve. In 1936, it started bursting. And so whoever was observing in 1936, saw that this object is going into outburst and got this beautiful light curve. The going up at the rise time was about a year. And then it's been an outburst ever since. So there are different types of bursts, but these are almost always discovered through optical monitoring. Optically bright means that they're at the later stages of star formation. So it would be these last two bursts that are visible optically after the star has already gained most of its mass. And that's still true. Most bursts are now being detected by Palomar and Gaia. And then I wanted to point out that Ninan also did some beautiful work with SALT a few years ago, trying to understand some of these bursts. You can do all kind of beautiful physics trying to understand the disk and outflows. And so we wanted to get to the earlier stages when the star is gaining most of its mass. And so that led us to develop this sub-millimeter survey. It's through the East Asian Observatory. We're using JCMT, a single dish sub-millimeter telescope. And this is the first long-term sub-millimeter monitoring program. So before this survey, people kind of thought we were crazy, that we'd never be able to see sub-millimeter variability. There were some technical challenges to be able to get to flux calibration that would allow us to see sub-millimeter variability. And then a lot of people just thought that the timescales would be too long.
So Greg, there seems to be a question.
Yep.
Vineet, can you go ahead and ask your question, please?
Yes, hello sir, I am Vineet from PRL. I have one question to ask. So what are the possible reason for these FU bursts? Like there is a sudden increase in the accretion rate and they are very intense. So what can be the possible reasons?
So they're caused by disk instabilities, and apologies for not digging into this deeper. I think more of an observer than as a physicist. But it must be some sort of instability in the disk. These shorter bursts, EX loop and some others, last for about 6 months. And so you could think of this 6 month as a dynamical time. So something happening within a few tenths of an AU. And that maybe changes in how the stellar magnetosphere interacts with a disk, or it may be something else. These FU Ori, the dynamical timescale, or the timescale of that burst, is centuries. And so that puts you out a bit further if you think in dynamical times. Models put it, depending on the type of instability, maybe at 1 AU, maybe out to 20 or 30 AU, although this FU Ori disk is actually very small. And then there are different instabilities that can affect the disk. An easy one is if you have binarity, maybe the binary is in some eccentric orbit, and that could excite periods of strong accretion. But then there are many, many other instabilities. Probably my preferred model is a combination of a gravitational instability. This is work by Jehan Bae and Jiahwan Zhu. We have a gravitational instability that then needs to heat up the disk, that then leads to a thermal instability through the MRI or some other instability. And that leads to a lot of material going from outer parts of the disk moving inward and eventually reaching the star where we'd see this. And these instabilities are very, could give a whole talk on just that one subject. So we've been trying to look for these instabilities at younger ages. And so we started this JCMT transient survey, and we've now been going for almost 5 years now, and we'll be going up through 7 years. We started out with 8 regions, looking at them once per month, and we've since increased that to 14 regions, where we've now added some intermediate mass star forming regions. These 8 regions are all nearby low mass star forming regions, and they're all famous: Orion, Ophiuchus, Serpens. And so these are some co-added maps. We're getting very deep co-added maps. And we're also getting some variability. So on the top 4 objects are all objects where we're detecting submillimeter variability. And on the bottom are stable objects where there's no variability. We're getting down to about 2% precision, and we're pushing technical improvements forward where I think we'll end up around 1 or 1.5%.
So Greg, this 2% that you're talking about, is it absolute flux precision? Or?
It's a relative flux calibration. So if we're putting any point on an SED, there's still the absolute 10% calibration uncertainty. And we're not really worrying about that. What we really wanted to push on was the relative uncertainty from one epoch to another.
Yeah, I understand that.
So that
the
uncertainty.
Points, the points in this for the same object, the points in this light curves are on different days.
Yep.
So
these are
the same flux calibrator on each.
Yeah. So we're doing what optical people would call differential photometry, just adapted for submillimeter. So if you look, say, in the upper right, Ophiuchus, you can see that there are kind of 3 or 4 main blobs, and then there are a lot of other point sources in there. And so we use these point sources to measure stable calibrators. And sometimes our calibrators become unstable, so we have to kind of keep iterating on that.
But use the same sources to calibrate on each day.
Yeah, that's right.
Okay.
And we're able to get down to 2% by doing that. We need to do more complicated things to get down to 1%, autocorrelation functions and things like that. And so we're getting these beautiful light curves. The difference in the y-axis isn't huge. And the optical, for example, the source on the left, well, we don't see it in the optical, but at shorter wavelengths, it would change by about 2 mags. And this is, just a few tenths of a mag. This is a 40% change. But a 40% change in the submillimeter is huge and corresponds to a much larger change in luminosity. You can see a couple decays and one that, maybe went up and then is going back down. So we get different types of light curves in here. Some seem random changes. Some seem linear, and some are kind of periodic or quasi-periodic. So the source on the left has been our favorite source. And we're now calling it Young Faithful because it has these kind of quasi-periodic bursts. They're not periodic, it's not perfect, but about every 1.5 years, it has these bursts and then it decays. And in red, you see our 850 micron light curve. And then in the other colors show JHK. So this source is a very young protostar, but we think its outflow cavity is pointed towards us, so we can actually still see it in the near infrared. And by comparing these light curves, we can understand kind of more of what's happening in the inner disk. And interestingly, the rise time and the decay times are always about the same. Each of these bursts and decay cycles, the rise lasts for about 1/10 of a year, and then the decay is about 9 months. And this is beautiful work by Young-hee Lee and the co-PI Doug Johnstone. And Young-hee works with Jung-eun Lee in Korea. He's a PhD student. So we can understand through these SEDs, through changes at different wavelengths, how the star and inner disk is changing, convert it to a luminosity, and start to understand these bursts. So ideally, we want to go back to the luminosity problem when we're finished. Our fields are still very small, so we're not going to be able to say very much about the luminosity problem just from our fields. But hopefully, we're developing the techniques where larger surveys in the future will be able to really probe the luminosity problem through submillimeter variability. And the way we're doing that is by, or the way that we'll do it, that's still insufficient, but making progress, is through analyzing the light curves and trying to understand how variable they are, and then putting that into some modeling context. And you can see here, this shows kind of the slope of variability versus the peak flux. So you can imagine the brighter the object, the easier it is for us to detect variability. And for the bright objects, about half of our sample is variable. For the faint objects in our sample, none of them are well, one of them is variable, but we're much, much less sensitive to variability at the faint end. Most of the variability we're detecting is at the 5 to 10% level, so very small changes. But we think that if we were able to go deeper, more accurate, maybe all of these faint objects would also then become variable.
So Greg, do you attribute this variability to a change in the luminosity of the illuminating source inside, or something else happening in the envelope?
So we attribute it to a change in the central source. That change then propagates through the envelope, it heats the dust, and then we get more emission from that heated dust in the submillimeter than we would otherwise. So we think we're probing the central star's luminosity, just indirectly. And if there are any stellar flare people, we also got a cool result where this is the first coronal flare detected in the submillimeter, and it's whopping bright. And we were able to even catch a decay during our 30-minute integration. So this is probably the most luminous coronal flare that's ever been detected.
Why do you call it coronal flare?
So it happens in the submillimeter, but the spectral slope suggests that it's kind of radio synchrotron emission. And I would assume that that would be something that happens on the star. So same as like radio flares would happen for flare stars or for the sun, but many orders of magnitude brighter than that.
So, but you're sure this is not happening at the base of the outflow or anything?
Probably not. The time scale, so we see a decay during the 30 minutes of our integration. So that if you convert the time scale to a distance, it's something that's happening over a very short distance.
Okay.
It's on the star. It's not just some outflow thing happening. Those are kind of the problems that I've been thinking about for protostars. Still have some disk evolution and planet formation to talk about. And then after that, I'll briefly touch on understanding star formation through class 3 sources. So protoplanetary disks is where planets form. And people have been asking for quite some time, how would a planet in the disk change how we see the disk? So these are simulations by Jiahuan Zhu, but people started asking this back in the 80s. What happens when you just drop a planet in there? How will that affect the disk? And so before ALMA, our understanding of these processes really came from Spitzer. And our understanding was pretty basic at that time. There were a few things that people could do. First would be go to a cluster of young stars, measure the fraction of stars in that cluster that still have a disk, measure the age of that cluster, and then you can put it on a diagram like this. All these data points are different clusters, and you can see that about half of the disks survive for about 3 million years. A few random disks dissipate very quickly, and a few random disks last for 10 million years or longer. And then people could start looking for traces of planet formation through the spectral energy distribution. If you just have the star, you're on the Rayleigh-Jean's tail, it just kind of falls off, and the photosphere gets fainter and fainter. But if you then throw a full disk in there, the emission in the infrared that you get is quite bright, and that emission traces the warm dust in the disk. If you take out an inner cavity, you're taking out that warmest emission, and that warmest emission is emitting at shorter wavelengths in the infrared. So instead of getting a full disk, as in gray here, you take out all that warm dust, and that leaves a gap. And so this was kind of the state of the art 10 years ago at Spitzer, where people were inferring inner holes in the dust through these spectral energy distributions and thinking, maybe those are places for planets. This is an example, C.S. Cha. This work was actually first started back in the 80s by Steve Strom and Karen Strom in Skrutsky, but then became an industry when data became much better with Spitzer. And you can see C.S. Cha, the emission is much fainter than what the average disk is in this star-forming region. And then before ALMA, there were a couple of cases where these inner holes were actually measured in millimeter-sized dust. So instead of just having a spectral energy distribution, people could go in and see that there's actually an inner hole in this distribution. ALMA, close to a decade now that ALMA has been operating, has been really revolutionizing for understanding protoplanetary disks. It's the best stuff coming out of ALMA, I think. And ALMA is a large interferometer. Your spatial resolution goes as lambda over d, and so when you're at 1 millimeter, your spatial resolution is terrible. So you need to improve the diameter, and you do that through interferometry by separating these dishes by kilometers. So the longest baseline is 15 kilometers. And then this is very high up. It's 5,000 meters on the Chajanator Plateau, one of the driest sites on Earth. And so you get through a lot of the atmospheric telluric absorption that would otherwise be a problem at any other site except Antarctica. So it's been amazing. The first surveys were kind of these complete surveys of star-forming regions where all you could get is this flux, unresolved spatially, and there'd always be a lot of scatter. You'd always find kind of a flux versus mass relationship. These fluxes were usually beneath where you'd expect a minimum mass solar nebula to be. And there are all kind of interesting uncertainties that go into these masses, which may explain why the masses are almost all below the minimum mass solar nebula. And these are still unresolved, and it's unclear how exactly to resolve them. But dust opacities are always uncertain. Scattering has become more and more interesting. For CO, optical depths are a mess. And so there are a lot of problems in understanding these large unresolved observations. And the real ALMA revolution for disks has come not in unresolved population statistics, but in looking at dust structures. So these are 3 examples of different types of substructures that we see in protoplanetary disks. Something to keep in mind whenever you're looking at these images is that the large dust grains are drifting to the local pressure maxima. So what we're seeing is the millimeter-sized dust grains, but we're also seeing the pressure maxima in the disks. In some cases, it forms rings, some cases these weird peanuts, and then in other cases, spiral arms. So this was the first really amazing disk that came down from ALMA, where you saw these beautiful rings. It took me a couple hours to convince myself that this was not an artist drawing of H.L. Tau, but it was actually the real image. Just amazing. And this was really surprising. H.L. Tau is a very young star. Everybody thought that the disk would be very viscous. Viscosity spreads everything out. And instead, we see these rings at very young ages. On the other side, at 10 million years, so a very, very old disk, we still see these rings. This is a beautiful image by Sean Andrews. Sometimes we see spirals. Sometimes this is gravitational instabilities. Spirals may also be excited by a companion. And then we see these dust traps where all of the millimeter-sized dust is concentrated in azimuthally asymmetric regions, even though the rest of the disk, the gas, may be symmetric. So we wanted to know how frequent these were to try to understand dust evolution. And so there were two surveys, one led by Sean Andrews, just going very deep, getting amazingly beautiful images. And I could look at this all day. Our survey was very jealous of these images, just unbelievable. These are just beautiful images. And you can see the most common thing are rings, but then there are also some weird asymmetric structures. If you look 4 across, 2 down, you get this weird bright peanut thing.
Greg, there is a question in the chat box,
Okay.
which is, why do the accretion disks look like rings? Why are there gaps?
Yeah, so ask that again in a couple of minutes. So that was the Andrews survey was looking at the brightest disks. We decided to do kind of, a survey that's a little bit cheaper, a little bit lower spatial resolution, much less observing time, but be unbiased to flux, so we get a lot of faint sources, and relatively complete within some spectral type window. And you can see again, we see a lot of these rings, and then there are a lot of very compact disks. So we wanted to understand, what's causing these rings. There were 2 competing scenarios, and one was maybe something to do with chemistry and ice lines. But these rings are kind of distributed randomly in the disks. There's no obvious thermal reason why the rings would be at the locations where we measure them. And so the most plausible result is that if they're just random, well, planets happen at random places. And so we can actually estimate what the masses are by the properties of those rings and using hydrodynamical simulations. And so instead of putting them at ice lines, we think that they're probably planets. And the population of planets that we detect are below the detection limits of current surveys of exoplanets. So there's no discrepancy between what we're seeing and the known population of planets. And so we think these gaps are just being carved out by planets going around the star and carving out the gap. And there have been this really exciting case of PDS 70, where a planet has actually now been detected in one of these systems, where there are 2 planets. One was detected with sphere in the near infrared, and then 2 that have been detected in H alpha, and the one that was not detected in the near infrared was detected in the submillimeter, and it's located right on the edge of this dust ring. So people are now starting to see these planets that are in formation, that are actually carving out these rings. And then there's another way of inferring planets through CO channel maps. And again, where the location that they infer the planet is the location of this gap. So this is actually my favorite work from Christoph Pint from ALMA, just beautiful use of looking at CO maps. In our unbiased survey, we didn't just detect rings, we also detected a lot of very small, smooth disks. In a few cases, these are from binaries, but there are other cases that aren't binaries where the disk is very, very small. And so we're still trying to understand why they're so small and compact. And hopefully we'll be getting data on this when ALMA comes back online. But one possible explanation is that you get very efficient radial drift. This is from a paper by Stefano Facchini, where all the millimeter dust drifts to the center. You don't have a ring set up, maybe you don't have a planet, so that dust just drifts until it can't drift anymore because of sun trap, maybe a planet at an unresolved location. And this is going to be very exciting, I think, with a 30-meter telescope, where we'll be able to get images like those on the left. We'll really be able to study these planets' information, but in much, much finer detail and much more sensitivity than what we can with the current class of 10-meter telescopes, with much finer spatial resolution and much deeper. So very briefly, a few problems with ages of young stars. I don't have all that much time to dig into this, but it's a problem that I like thinking about quite a bit. On this sort of plot, we want to relate things about disks, things about protostars, and we want to understand them on an evolutionary sequence. So this very basic plot shows just, is there a disk, yes or no? But we really want to understand like how disk mass changes with time, mass accretion rate changes, how disk substructures change with time. We want to place them on an evolutionary sequence so that we can use the observations to understand the physics that is changing the disk. And so in principle, that should be easy. We just go in and we measure the age and mass of a star by measuring the luminosity and the temperature, put it on an HR diagram, right? People have been doing this for 100 years. For pre-main sequence evolution, the Hayashi contraction is vertical. And then for solar mass stars and above, when that interior becomes radiative, then the evolution is on the Henry track and goes horizontal. Measure temperature, measure luminosity, put it on here, get an age and mass, easy. The problem is that whenever you do this for a cluster that you think all the stars are about the same age, there's a huge luminosity spread. So how much of this then is real and how much is just uncertainties, how much is just differences from star to star? So a first problem is this age spreads or luminosity spreads in young clusters. I thought that kind of empirical improvements in HR diagrams would change this by doing the temperatures and luminosities better. So I put a lot of work into this a few years ago. Carlo Manara used XShooter to really do a much better job with this, but these spreads still exist. The second problem with understanding ages is that there's a mass dependence in the age. So the higher mass stars will always appear older, even though they are not older. This is some sort of problem with the models. So people had always adopted these younger ages for pre-main sequence stars that you get from the low mass stars. But the intermediate mass stars tell a different story and give you different ages. And so something that can do is it can move this diagram, the half-life time of a disk, by a factor of 2. Maybe you have a factor of 2 longer to form your planets. And so people have been taking this idea more seriously, but there's still too many problems with the models to know which one is right, to know whether these are older or younger. The main problem seems to be initial conditions, where it's unclear how much entropy the star starts out with. It's been work, especially in the past 10 years, by Isabelle Baroff, but it goes back to Steve Staller in the 1980s, where you can start out with bigger or smaller stars. And the contributions that I've been thinking about are more still in the uncertainties, but what happens if you have a spot? So we took one of the most spotted stars, like calcium-4, in my postdoc, Gully Santiago, put it on HR diagrams, and it moves depending on how you're measuring the effective temperature, whether you're including the spot or not. It moves a huge way from 4100 to 3200. So we don't understand spots at all. Gonna move past this for time. And so I think spots are a major uncertainty. And I think that Gaia and better understanding of nearby star forming regions and more distant star forming regions is the key to giving us much better ages and understanding our local star formation history. There's some just beautiful maps that Gaia is making. People are doing some amazing work. My own small contribution was trying to understand serpens, where we see several bursts that have happened over the past 20 years. Ujwal is working with Manoj and some other people, also doing some really beautiful stuff with Gaia. I love all the Gaia things that are coming out. And I'm hoping that in addition to other amazing things that Gaia does, that it's going to help us improve masses and ages of all these young stars. And then further afield, we want to understand that star formation in the context of, how does a star form? Is it triggered? And what happens in different environments, high radiation fields, low metallicities. So this is from Jessie's work from a few years ago, where she looked at a region in the W4 bubble that seems to be triggered by understanding the stellar population. And there's really amazing work going on in India right now. Dewanga and Oja, Manashamal and Pandey, some other people. And so one of the things that I really wanted to do, if I was able to get there, was talk to all of you about the amazing work that you're doing. And last but not least, the next few years, I'll be working quite a bit on an ultraviolet survey of young disks. So this is something that I didn't have time to really talk about. But there's this program, Ulysses. It's a director's discretionary time program, legacy program from HST, where 500 orbits are going into mostly FUV with a little bit of optical spectroscopy for young stars in order to understand the disks, the accretion flows, and the accretion-driven winds. This is on the bottom. You see a little cartoon of what an accreting young star looks like. And there's all kind of diagnostics that are only detected in the ultraviolet. You have carbon-4 absorption, there's a lot of winds, and then directly looking at the disk surface. And so this is a huge program, 500 orbits, something like 50 objects, including some monitoring. And something that's really critical for this is getting simultaneous ground-based photometry and spectroscopy. So there are major efforts from that. And Odysseus is an open team for archival research, being led by myself and Catherine Espaillat in the US. And so this is a large effort to analyze the data, coordinate publications and who's working on what, and then trying to get a really robust set of photometry and spectroscopy. I think we have one person in India, Neelam Panwar, and it's an open team. So those of you who are interested, if you think you might be able to contribute something, observations, labor, things like that, please contact me. And so that I'm running a little bit late. So I'll just leave my conclusions up there. I also have my email down below if you're interested in contacting me, either for science reasons or if you're interested in postdocs at the Kavli Institute. And most importantly, it's been a stressful year for all of us. I'm away from my home in China probably for what will be a year. And I think, just going outside is very stressful. And it's been painful watching India's numbers of cases just go up and up. US, it's by choice. But there, it's very painful for me to see. So please, stay healthy and sane. As hard as that is to do in this very stressful environment. Do good work, but also please keep yourself healthy and sane as we live through this crazy period. So thank you very much for taking the time in this stressful time to listen to this talk, and happy to take any questions.
Saurav, I see your hand is raised, but there is a question in the chat box. So I'll first take that and then come to you, Saurav, and then followed by Oja. Before that, let me thank Greg, and I should also tell you that it's Greg is in the US now, and it's early for him, so he was kind enough to wake up early to give this talk. So thank you, Greg. Thank you, thanks a lot. So let's take
thanks for this opportunity.
Thank you. So let's take the question in the chat box first. It's by Swastik Shinde. Swastik asks, can you explain about the detection around the stuff of Fomalhaut? At first, it was detected as there is a planet. Later, it disappeared. What really happened? The article published suggested that it was a ball of dust which dispersed. Could you say something about that? Greg, do you think?
Yeah. Even from the first detection, I think that there were some skeptical people. And it was really weird when it was being detected in the optical, but not in the infrared, where the planet would be much brighter. And so it seems to be some sort of ball of dust that's being seen in scattered light. And scattered light is usually stronger in the optical. Whether that ball of dust is around some low mass planet that is not detectable, I don't know, maybe. And it sounds like whoever was asking the question probably knows more than I do. But it seems like the emission we're detecting is not from the planet. I don't remember the work well enough to say whether that means that there's a planet that we just can't see, or whether there's something else weird that happened in the Fomalhaut disk where we see this clump in scattered light.
Okay, so the next question, Saurav, go ahead.
Hey, Saurav.
Hi, Greg. It's great to see you.
Good to see you again.
I'm very glad that you're doing well. I mean, the whole world is going crazy now. So I actually had two questions. The quicker question, I think, the first. So you mentioned that in the ONC there are these confusions if you put them in the color magnitude type diagrams, and there can be a range of different luminosities for the same temperature. So the age may have a spread, or there is at least a confusion in what how old these stars are. So based on your work, do you think that it's a real spread in ages of star formation, and can we put constraints on what is the duration for the star formation in ONC, or is it just something related to the actual star formation process where the luminosities just change so much it's hard to constrain the ages accurately?
Yeah, I think that in part the answer to that is still a little bit unclear. But I think, like, if you look at this diagram, you get an age range between like 500,000 years, which could be real, out to 30 million years, which is not real. So these older stars are definitely not that old. And so it could be, I think spots kind of are doing weird things and confusing us. There are extinction problems, which could change how we're measuring the luminosity. Contamination could be an issue sometimes. And then there's also this idea of, that some stars can start out smaller depending on their accretion histories. I actually think that the accretion history isn't all that big of a deal. I'd like to see more work on that empirically. Everything that we know kind of comes from models that say maybe it's a problem, maybe it's not. So I think we can do more empirically. And then in order to get kind of a real age spread, we would need to understand both the empirical uncertainties in temperature and luminosity, and we would need to understand those model uncertainties. So I think that getting an age spread through HR diagrams is probably too uncertain to be reliable. It's telling you something, but the luminosity spread isn't necessarily telling you that there's an age spread. So I think that there are probably other ways to do that are better, potentially including Gaia dynamics or something else. I think there'll be better ways.
The other question I had was about the rings. So if I remember correctly, Yoram Litwick and his student, they were looking at some eccentric disk models. And apparently, even without planets, these eccentric disks can create some resonances that can create this low luminosity ring-like features. Can you comment on that? Is it ruled out? I haven't followed it.
I'm not sure. There's something like probably 35 different models for these rings. So honestly, I haven't followed each and every one. The most prominent one, people were kind of focused on whether it was some chemistry thing or whether it was planets. Planets make the most sense. But there are plenty of others. These are something you said was low luminosity, and these are actually pretty high contrast features. And so I'd need to understand more of what they were predicting. But these are high contrast, right? Like look on the bottom, it's 1, 2, 3, 4th. The 4th and 5th, I mean, those are, they're very thin rings, and there's really almost no dust in between. And I don't remember offhand what the contrast ratios are, but they're probably between 10 and 100 for a lot of these systems. So it may be that their explanation could explain a few of them, but not all of them.
And in all these models, it's usually assumed that dust is coupled with gas, right? Is this so correct?
No, I think that that assumption gets broken both observationally. It's very clear that dust and gas have different distributions. And also in the models, people are now doing kind of full hydro where the dust and gas distributions are decoupled from each other, or they're coupled, but in weird ways. And so this goes back to Weidenshelling in the 70s, where looking at dust drift, the gas pressure feels, or the gas feels a pressure that the dust doesn't, and so that pressure means that the gas is rotating slightly subcaplarian. And then that has an effect. The gas and dust then collide with each other, and that causes the dust to drift very quickly. So even back then, they realized that dust and gas, if you have a disk, people didn't really believe in disks back then. But if you had a disk, the gas and dust wouldn't be coupled. And so now I think most models that do both the gas and dust have them is, semi-coupled, but in different distributions. And I think the advances over the past 5 years and for the next 5 years aren't just in the hydro, but in trying to do global simulations with all of the complex, non-ideal magnetic effects that happen in the disk. There's been a paradigm shift over the past 5 years on what governs the gas dynamics in the disk. But those haven't really been done on a global scale. They've just been done in shearing boxes.
Okay.